All right, let me tell you where we're going. I'm going to give you in the next half hour or so some detailed evidence, and I apologize now for the details. There will be some of them. I'll try to make them accessible, pointing unmistakably to intelligent design in biology. Unmistakably in the sense that the evidence is so strong, it's really the only reasonable interpretation of what we see, that is, that it was designed. Now, you might have a skeptical moment and say, but Paul, I know that the majority of the scientific community, of the biological community, rejects intelligent design. So if the evidence is so strong, why don't they accept it? Well, that's the second part of my subtitle. You can see there's a play on words there. We're going to look at the evidence of nature, but also the nature of evidence. Evidence is a transaction between the world and you, and in fact, other people. In Illinois, where I live, we have an unhappy practice of putting our governors in jail. Our last governor, Rod Blagojevich, as many of you know, is doing some very hard federal time right now. There were 2 trials for Rod Blagojevich. The first one ended in a mistrial. They had to do it again. Now, how is a mistrial even possible? Well, it's possible because a member of that jury said, I am unpersuaded by the evidence, and there was nothing anyone else in that room could do to get her to change her mind. And they had to tell the judge, we have a mistrial, we've got to do it again. So think about what evidence is as you go through this talk, and at the end, we're going to come back to this question and see why it is that this evidence is unpersuasive to the majority of the scientific community. And I'll tell you, I'll give you a sort of forecast. It has nothing to do with the evidence itself, but what we're going to let that evidence tell us. All right, it's funny what you remember from college. I used to go to the office hours of one of my mentors. He was a brilliant atheist philosopher of science. I won't mention his name because he's still alive and very active, and these were private conversations. But he was a brilliant man. And I would be scared going to see him because I knew that he was going to try to take my arguments apart. But not only did I have to face this guy, who actually ended up recommending me to graduate school, and face his intellect, I had to look at this photograph. Now, many of you know who this is. This is one of the most influential intellectuals of the 20th century, Bertrand Russell. A brilliant logician, philosopher, social critic, educator, and atheist, whose ideas strongly influenced 20th century philosophy and science. Near the end of his life, Russell was asked by a very brave reporter, I would not have the guts to do this, but someone asked him, what would he say if after death he realized his consciousness was continuing and there was God standing looking at him? In other words, they said, Dr. Russell, Lord Russell, what would you say if you met God after your death? And he said, I should reproach him for not giving us enough evidence. In other words, I remained an atheist throughout my life. He played around in his late teens with theism and then rejected it and then was a lifelong atheist because the evidence in some sense was insufficient to show God's existence. So think about it this way. Here's Atheismville. Very nice town. Kind of like Sweden, you know. Here's Belief Land. And you have an atheist friend, or maybe he's an agnostic. He's not sure if he lives in Atheismville. He might be in the suburbs. And you're going to try to persuade him that God is real. Christianity, that's a bigger challenge. You just want him to acknowledge that there is a God who made the universe. So you sit down, there's the road, by the way, connecting the two. You sit down in your car, turn on the ignition, and he looks at your evidence gauge and he says, we're just never going to get there. You've barely got a quarter tank. That's a long road. You've got to get that red all the way up to the top of that gauge if you expect me to get over to Belief Land. This view treats evidence quantitatively as something you can kind of pile up, and at a certain point, it's compulsion. The atheist says, all right, you've accumulated enough, now I have to believe. Now, I've told you I'm skeptical of that view of evidence because that does not recognize the role of the individual in evaluating evidence. In that failed Blagojevich trial, 11 people were sure he was guilty. One was not, and it wouldn't matter how high they piled it, she just wouldn't change her mind because of that transaction. Now, we need to notice that Russell's view that there wasn't enough evidence is actually rather recent in human thinking. This is Isaac Newton, one of the founders of Western science, and in his book, The Optics, in fact, right throughout all of his writings, Newton was absolutely sure that the evidence pointed to a creator, a being, incorporeal, powerful, omniscient, who made the world and everything that we see. And science itself, he didn't give it that name, he called it natural philosophy, but science itself had value in part because it pointed us towards a creator. So you might say, all right, what happened to the evidence? What happened between Newton and Russell? Well, here's a little timeline. We can put Russell in there in the 1960s saying, I would reproach God for not giving me enough evidence. We can put Newton in there at the time of the scientific revolution. Something happened in that intervening period to change how science viewed the evidence. Well, what really happened was the Darwinian revolution. In particular, the introduction of the mechanism of natural selection to explain what appeared to be design in living things. So for Newton, there was clear evidence of design in biology. It wasn't there for Russell, and that's because Darwin's proposal of natural selection changed how people viewed living things. In particular, it seemed to offer a strictly natural process for the origin of biological design. So, Richard Dawkins puts it this way: the theory of natural selection provides a mechanistic causal account of how living things came to look as if they had been designed for a purpose. Came to look as if. In other words, you look at the eye of a salmon or the eye of an eagle, or you look at the brain of an octopus, which is rather sophisticated. They're like honorary vertebrates, they're so smart. Look at any biological design, and it seems to indicate that there was an intellect that put it together. And Dawkins says it only appears that way because natural selection now explains that we know better. And this view is very widely held by biologists. Ernst Mayr, for instance, who had a long career at Harvard, right up until 100 years of age, said natural selection is so important for evolutionary biologists because it seems to explain, or it does explain, the design of living things instead of, that is by a natural process instead of by divine action. So to understand what happened to the evidence, we need to look at natural selection and ask, does it actually explain what evolutionary biologists claim that it does? So that will be our little case study this morning. Before we get there, though, I want to give you a very interesting historical detail. Bertrand Russell had a very high regard for the power of the design argument. You know, there are several classical arguments for God's existence, the ontological, the moral, and so forth. He thought all of them had some kind of logical flaw. But when it came to design, he said, this argument actually works. It depends on what the evidence shows. So in this passage, he says, this argument says that there are features of the world that look like they were caused by a beneficent purpose. That is something with an intellect, a mind like ours. This argument has no formal logical defect. Its premises are empirical, that is, they're drawn from nature, and its conclusion is reached in accord with the usual canons of inference, the way that we do in science. So he says, the question of whether or not we're going to accept the design argument depends on comparatively detailed considerations. Now, what does he mean by that? What he means is you've got to look at the evidence in detail. So that's what we're going to do. We're going to dig deep and weigh what kind of cause can explain the biological evidence in front of us. And I want to do, as I said, a little case study here in a puzzle that Richard Dawkins and Ernst Mayr claim natural selection can explain. And that's the origin of animal body plans. Now, think about what you would want a theory of evolution to do. If you're a biologist, let's say, or just a curious human being, You wouldn't be content with that theory if it just explained to you why one moth had slightly more pigment in its wing than another moth. You want to know, where did the moth itself come from? Where did oak trees and blue whales and bacteria and human beings themselves, where did we come from as organisms? Well, that's really, in this instance, we're going to look now just at animals. That's the question that we'll look at. So here's a little worm, very, very small. It's about 1,000 cells in the adult. And you can find these worms, they're nematodes, in the soil. If you have a pretty powerful small hand microscope, you can see them. They consume bacteria. Here's a fruit fly, Drosophila. If you have overripe bananas, as my wife and I did this summer, unfortunately, we had a lot of these buzzing around our kitchen. They're actually very, very small, but quite beautiful. They have brilliant red eyes. Or there's the purple sea urchin, which if you go here at low tide to Laguna Beach, in a tidal pool, you'll see lots of these. They flourish along the Pacific coast. Now you'll notice that they don't have the same overall architecture. A worm's a worm, a fly's a fly, an urchin is an echinoderm. Fly's an arthropod. Their architectures are different. They're not the same kind of living thing, and it's not easy to interconvert them. So this is going to be a real challenge for evolution. Where did these different architectures come from? Okay, so if we're going to evaluate natural selection, we first need to understand how natural selection operates. Now, let me stress to you this morning, I think natural selection is a real process. We have lots of examples of it, in fact. My wife is a pediatrician in Chicago, and during her training, she was told to tell patients, don't expect, if you have a minor infection, to go home with an antibiotic today. Because we have a tendency to abuse antibiotics. We take them until the symptoms go away, and then we put the rest of the medicine in the cabinet in the bathroom. If enough of us do that over and over, that antibiotic is less effective the next time we need to kill some bacteria because of the power of natural selection. So natural selection is real. The question is, does it do what evolutionary biologists claim that it can? All right, so here's a little formulation of how natural selection works. 3 conditions have to be satisfied. The first one is variation. So we need differences. There's some tigers, and that poor guy on the left is saying, man, I got no stripes. I'm barely a tiger. I don't know what I am, but I got no stripes. That's variation within that species. You can see the differences there. Here are some stickleback fishes, again, all within the same species, and you can see there's lots of differences between those various fishes. And those differences between tigers or fish, or in this case, ladybugs, may make a difference to the number of offspring that they leave. And of course, if we look in our species, Homo sapiens, we have a tremendous variety of differences. Just within this auditorium, you look around, you see a lot of variation. So that's the first condition. You need to have differences. They need to make a difference to the number of offspring that you leave, more or less. So here's a little cartoon showing a trait in a single-celled organism. The yellow trait is favored under the selective condition that we've set up so that as that condition is maintained, the orange trait disappears, and over time there's a shift in the population until the yellow trait dominates, and you need to be able to pass it on. You've got to be able to transmit that variation to your offspring. If you can't, there's going to be a problem. But if those 3 conditions are satisfied, natural selection will occur as night follows day. Necessarily, you can count on it. So we go back here, you can see we started out with orange and yellow. That black bar represents the selective condition. We end up with just yellow because the orange creatures couldn't survive. You can think about this like 3 legs of a stool. You've got to have them all for natural selection to operate. But the bottom line for the example that we'll be looking at is if you can't leave offspring, you're a dead end as far as evolution is concerned. So think about it this way. Imagine someone with the intellect of Albert Einstein and the physique of Michael Phelps. Okay? Put those 2 together. Absolute brilliance intellectually, Olympic specimen in terms of their physical characteristics. One problem, that guy is sterile. His testicles are not producing any sperm. It doesn't matter what else is right with him. He is a dead end and invisible to evolution because he can't leave any offspring. Whereas Paul Nelson, who very obviously does not have the physique of Michael Phelps, my wife did the work. On March 16, 1992, in Beth Israel Hospital in Boston, we successfully passed on DNA to the next generation. So in that sense, I'm more fit than this hypothetical super intellectual swimmer. If you've got kids and you're not happy about your physical condition, just remember, you've got kids. You're fit as far as evolution is concerned. Now here's a problem for natural selection. The claims that are made on its behalf are rarely backed up with evidential support. Rarely. Richard Dawkins will make a claim like this, but if you actually go to the biological literature, as I do professionally, and look for the evidence where natural selection actually is shown to be causally effective in building eyes or ears or brains or wings or nervous systems, it's just not there. And in fact, this has been known for a long time. Even at the zenith, even at its most popular period in the 1960s, natural selection left many evolutionary biologists very unhappy. So Conrad Waddington, for instance, the man on this slide, was an embryologist who worked closely with the core of the evolutionary community in the middle decades of the last century to try to sort out evolution. And at a famous meeting in Philadelphia in 1966, he said, evolution, the textbook theory that we have, doesn't really explain what we want it to. What he called the whole real guts of evolution are left outside the mathematical theory. And by that he means the mathematical expression of natural selection. In particular, this problem is unsolved. It's wide open. And there's, of course, a greater variety of body plans. You come to recognize these even as a small child. You can distinguish a spider from a sand dollar. They're just not the same kind of organism. They have fundamentally different architectures. Of course, we belong to that group in the lower right, the chordates. If evolution can't explain the origin of these differences, the theory is in deep trouble. Deep trouble. Now, textbook theory, the theory that you would get in a public high school here or university at UCLA or USC, holds that all the animals stem from a common ancestor. That kind of funny-shaped thing in the bottom there called bilateria, that's just a fancy name for an organism with bilateral symmetry. We are bilaterally symmetrical by and large. An arm on this side, an arm on this side, an eye, an eye. You can put a dividing line down the middle of us and you have roughly mirror images on either side, even though our internal organs aren't quite symmetrical. That theory has never been demonstrated. Bilateria is hypothetical. There are two different ways of drawing it there. One has a few more details than the other. That's a hypothetical construct to tie together what are in fact very different kinds of organisms. And this problem, this unsolved problem in the origin of animals, is well known within the discipline of evolutionary biology. Wallace Arthur is an English developmental geneticist. I met him when I was a graduate student in Chicago. And in the late 80s, he was becoming very unhappy with textbook theory. And in a publication at that time, he said, we don't really know how body plans originate. And the examples we have in our textbooks aren't adequate. So what he calls there Biston betullaria, that's the Linnaean name for the famous peppered moth of England, which many of you may remember from high school biology. This is a classic example of natural selection in action where pollution changes the color of the environment such that the light-colored moths are preferentially preyed upon by birds because birds can see them, where the dark-colored moths have better camouflage. And what happens in that process is the whole population shifts. It's an example of natural selection, but Arthur says this really doesn't explain where the moth itself came from. Eric Davidson at Caltech up in Pasadena, in a paper a few years ago, said, what we see with things like moths versus the question of where moths came from, these are fundamentally different problems, as different as apples and oranges. And we cannot understand the origin of the moth itself just from the small-scale evolution that we see? Well, you can go back in the history of evolutionary theory in the last century and find the point at which the mistake was made. Now, it wasn't really a mistake. Anytime you do science, you have to make assumptions about the world. And the founders of textbook evolutionary theory said, let's assume that micro or small-scale evolution and macro or large-scale evolution are the same. Just add time to micro and you'll get macro. Dobzhansky, who was one of the founders of textbook theory, in the mid-30s said, we can't observe macroevolution. It took place over a long time. So what we have to do is take microevolution and extrapolate that over time. And he said, we'll do this reluctantly. We'll put a reluctant sign of equality between micro and macroevolution, and we'll push our investigations as far ahead as we can on the basis of that assumption, or what he called a working hypothesis. Now, the thing about a working hypothesis is it can turn out to be false. And I think that's what's happened. So here's Dobzhansky's view. We'll start with population A, let's say moths. We'll let time run, and what will happen is if the variation that is operating under natural selection continues to arise, we may get change that occurs, indicated there by the letter C, that we didn't anticipate on the basis of our starting population. But given enough time and enough variation, natural selection will relentlessly move that population to a new point. So micro equals macro, just give it enough time. Well, that's not true. And it's well known within evolutionary biology that it's not true. In fact, John McDonnell, the geneticist at Georgia Tech, called it a great Darwinian paradox. And he said, we've known this for 20 years, that micro does not scale to macro. Now, this was published when I was an undergraduate, and many of you in the room were not even born. This problem has persisted for a long time indeed. Now, that should alert your kind of philosophical radar. How can an unsolved problem in evolution that's central to the theory itself persist for so long? Well, I'll tell you, we'll come back to this at the very end. It has to do with what we're going to let the evidence tell us. All right, we'll come back to that. But the problem arises at the intersection of three ideas, or if you think of it, three different parts of biological knowledge. One is how animal development works. One is the theory that may be false, that all the animals are related by common ancestry. And then the third is natural selection. And the paradox arises from a conjunction of what we know from each of those areas. Think about it this way. What do we know from development? Well, we know how animals are built. Almost all animals start as a single cell, a fertilized egg. That's how you began your existence, me, and so forth. Most, not all, but most animals start that way. The earliest stages of that process determine what follows. Certainly, no human parent sitting in an obstetrics waiting room wants to hear the doctor come in and say, Mr. Nelson, your daughter has a macromutation. Your newborn daughter has a macromutation, because we know from our experience that those kinds of changes are destructive, because they usually happen early in development and cascade throughout the whole process. So, if we're going to change the form of an animal, you have to start early, because that's where the form is put in place. But now the paradox arises. Those kinds of mutations are the ones least likely to be tolerated by the embryo. The earlier you go in development, the more destructive mutations are, because they affect more cells downstream. The bad effects cascade downstream and typically destroy the organism. And this was discovered in flies as a Nobel Prize-winning piece of research by this team, Christiane Nusslein-Volhard and Eric Wieschaus, in the late 1970s and early 80s in Europe. As I said, what they did is they looked at the problem right at where these three circles come together, and what they did was a kind of reverse engineering. Using fruit flies, they disrupted their genes, marching down the chromosomes of fruit flies, disrupting genes one after another. Then they asked the organism, what happens if we hit that gene? Will you develop? So we start on the left with the egg. You have this long developmental process leading to the fly. And by disrupting genes and their protein products at different points in development, they asked the fruit fly, did you need that protein for normal development? Or if we disrupt that protein, that gene and its protein product, what will be the downstream consequences? What they found was quite remarkable. Now, I told you there would be details. This is one of the details. This is a figure from their paper in Nature that ended up winning them the Nobel Prize. And I'll tell you what it shows. The left-hand columns show the normal larval form of the fly. So there are 4 columns there, and the left-hand side of each of them shows, if you will, the maggot form. It's quite small. It's very hard to see with your naked eye, but you can see it quite easily with a low-powered microscope. That's what a fruit fly maggot normally looks like. And the sections that are colored in pink are the sections that will be affected by the mutations that they induced. Now, the columns on the right are the embryos that have been mutated. And you can see that their form is very different than the normal form. It's truncated, in some cases it's much smaller. All the embryos in the right-hand columns are dead. They are not going anywhere, because the consequences for normal fruit fly development are so severe that it destroys the organism. And this is, in fact, how they figured out how development worked. Perturb it and reverse engineer it. Disrupt the process and then look at what is affecting what. And they quickly realized that if you want a fruit fly at all, you cannot perturb its early development. The problem is, for macroevolution to occur, that's exactly where the mutations have to take place. Hence, you have this great Darwinian paradox. In order to macroevolve a species, if you will, you've got to have viable early acting mutations. Yet those are the ones that are by far the most destructive. Which means that natural selection cannot operate. Natural selection, even though it is a real process, is powerless to effect macroevolution because the kind of variation that it needs is too destructive to animals. Ann Gager, who's a developmental biologist, developmental and cell biologist that I work with at Discovery Institute, Ann and I have compared this to what we call a magic bridge. Okay, this would be right at home in any Indiana Jones movie. The bridge is magic in the following sense. You start on the left and you start walking out on the bridge. As long as you keep moving towards the right, towards the other side, the bridge will be there beneath your feet. The minute you stop or look over the side, the bridge disappears and you fall into the chasm. You can see how it would fit in a movie because, real bridges aren't like that, but development is very much like that. Because only on the right, only on the far side of that bridge does reproductive capability arise. Yet reproductive capability, being able to make copies of your genes and pass them on, is a necessary condition for natural selection. So how did natural selection build that bridge of development when one of its essential conditions is way over on the other side? This problem has never been solved by evolutionary theory. And it's not because natural selection isn't real. It is real. It just isn't the right kind of process to build living things where they didn't exist before. In particular, to build animals where they didn't exist before. And the consequences for the Darwinian hypothesis are profound. I've showed you this slide before. This is what you would get in a textbook. It says that all the different animal groups came from this unknown common ancestor that we call Ur bilateria. Ur, by the way, is a prefix meaning original. You see it in biblical studies, referring to the Ur texts that gave rise to the books of the Bible that we see. So that original bilateral form, if it was an animal, probably had about a few thousand cells, the same problem would arise. If it was an animal, it would have gone through a developmental process, and to change it into an arthropod or an echinoderm or a chordate, in other words, one of these different architectures, would require disrupting its early development, and you'd have exactly the same problem again. There's no reason to think that things were different in the Precambrian than they are today. Well, I told you, this was a problem that I first encountered as a student, much skinnier and with a lot more hair. A long time ago, I'm telling you. It's well known. It's a well-known problem. So John McDonald, in this paper in the early 80s, and this is another detail, there's some technical language here, let me translate it for you. He's saying the genes that we see in populations today that obviously vary, and you look around this room, there's a lot of variation. Hair color, height, eye color, you name it. Homo sapiens has a lot of variation. Those genes don't affect the overall body plan. What doesn't vary? The genes that build your brainstem. The genes that give you a heart that's connected to your lungs. The genes that give you a spinal column and so forth. Variations in those fundamental systems don't happen because they have to happen early, and when they happen early, the bad effects cascade downstream and the organism is destroyed. You certainly know this from your own experience, and you can see it not just in Homo sapiens, but for instance, if you breed dogs, there are certain kinds of variations that species simply will not tolerate. Eric Davidson has been quite outspoken about this. In a paper last year, he said, textbook theory gives rise to lethal errors. You don't have to read all of that. I'll tell you what he's saying. He's saying what we see as viable variation in populations today does not affect macroevolution. To build animal body plans where they didn't exist before requires a completely different kind of theory. And he said, what you learn in a textbook, look at that, oh, it's not there anymore. The last sentence of that statement was, all of the assumptions of textbook theory are basically counterfactual. Andreas Wagner, who is an evolutionary biologist in Zurich, said, we don't know how natural selection operates. In this article, again from last year, he said, natural selection alone is not sufficient. It may explain the survival of the fittest, but it cannot explain the arrival of the fittest. All right, bottom line. Research on evolution done within the neo-Darwinian framework over the past 30 years has discovered that framework is actually false. And right now, if you go to an evolutionary biology meeting, as I do, with regularity, you will find people talking about this. It doesn't make its way into PBS specials or into textbooks or into the public face of science, but believe me, it's quite real. So where do we go? Well, it's time to go back to the philosophy of science and that second part of my subtitle, the nature of evidence. If you see something like this and you take it seriously, it tells you something about nature herself. It tells you to look for a kind of cause. If you're going to build that magic bridge of development, well, where once that egg begins to divide, it's got to get all the way over, in our case, to the trillions of cells that you see in an 8-pound baby. That kind of process is telling you, look for a particular kind of cause, one that can do the following, that can aim at a distant functional target. Natural selection is very powerful, but it has no foresight. It's powerful, but very, very dumb. It cannot look into the future to build something that will be needed in the distance. What kind of cause can reuse modules? You know, the proteins in your body are reused over and over and over in different settings. It's remarkable that the number of proteins you have is not that much greater than the number of proteins in that worm I showed you earlier. It's remarkably close. They have about 19,000. We have somewhere in the area of 22,000 proteins. Yet, you are here on Sunday morning and the worms are out there in the soil. There's a world of difference between you and those worms, and that's because we have a huge amount of so-called junk DNA that's not junk at all. That is a very, very sophisticated code for reusing those proteins to build what you have that makes you Homo sapiens. What kind of cause can build different systems that are different right from the start? What I call here primary discontinuities, where the system tells its parts what to do. You know, there are proteins in your body that are identical to those in a fruit fly, by and large, maybe a few amino acids different. But in your body, those proteins will build a compound eye, a camera eye. In a fruit fly, they'll build a compound eye. What you've got there is the system as a whole telling its parts what to do, top down. Well, this is what can do that. Universally, uniquely. This is the only kind of cause that can accomplish what we see. Now that's the evidence. What are we going to let it tell us? Now we run into a philosophical barrier. It's not a scientific barrier, because the scientific evidence is unequivocal. It's a philosophical barrier, and that's the worst kind of barrier to have. Because if you can't change it, if you can't find a way of changing that barrier, it doesn't really matter what the evidence is. The philosophy is going to stand in your way. And the philosophical barrier comes to us from the 19th century. It was introduced by the Darwinian Revolution itself as really a more profound consequence of Darwin's ideas than the theory of evolution, because it's at a much deeper level, changing the nature of science itself. In this essay in the early 80s, David Hull, who was a brilliant historian and philosopher of science at Northwestern, said, what Darwin did was not just to change how we thought about living things, but actually to change the nature of science itself. And what happened was a wall was thrown up around the evidence of biology that constrains the possible solutions you can offer to any puzzle. You can think of this like a city wall. Get inside the wall, you're allowed to work. Outside, you're a barbarian. And what the wall says is the following: the statements of science must invoke only natural things and processes, where natural is contrasted with intelligent. Here's a little taxonomy, or a little box of possible causes, if you will. You are an intelligent cause. Every time you answer a text message or an email, or someone bumps your car in a parking lot and leaves a note in your door with their phone number apologizing, for the damage, you make an inference where the box on the bottom, intelligence, is absolutely essential to what you do as a rational human being. And it would be that way if you were an atheist or an agnostic or a Buddhist or a Christian. It just wouldn't matter. All human beings use intelligence all the time in their daily life to explain what they see in the world. We know it's real. And the question is, are we going to be allowed to use that concept of intelligence in biology that made sense to Newton, that made sense to Kepler and Boyle and Galileo and the founders of Western science, was taken out of the toolkit of science in the 19th century, really, I think, to the detriment of science. So if we go back, there's our toolkit, restricted, and I think insufficient. But if we go back to our initial diagram here, let's say you've got the thing filled right up to the top. You've got all the evidence anyone could ever want. If you take that rule seriously of methodological naturalism that tells you you're not allowed to infer an intelligent cause, even if the evidence indicates that, this is pointless. There's no reason even to bother with it. The evidence will be powerless. And what happens is you have to say you can't get there from here, no matter what you show me. So when you think about this question of the evidence of science and belief in God and what it might indicate, realize that it's really not an evidential question. Yes, evidence is important, but far more important, in my experience, and I think you'll find this as well, is the influence of rules like this. The very worst philosophy of science to have, because it puts a screen between you and nature herself. God could have put a barcode in every living thing. God Incorporated, year 0, patent pending, I did this, pay attention. It wouldn't matter. If you take that rule seriously, it prevents you from seeing the evidence that's there. This kind of evidence that I think developmental biology reveals. Bottom line, natural selection explains almost nothing about macroevolution, for reasons having to do with natural selection itself. And if you contact me, if you email me, I'll bury you in articles, if you have the patience to read them, from the primary scientific literature explaining why this is so. So you've got the Saddleback 35-minute version. There's a longer version going into more of the details.